we start off with a point xy in the plane. Corresponding point on the graph of z equals f of xy. The point being xy, f of xy. If we come out some distance delta x and so, or through some displacement delta x in the x direction, displacement y in the delta y direction, we can do the polytope thing, and we get approximate tangent vectors tangent to the surface, because from this point to this point is a chord along the surface. If delta x is very small, that chord becomes very close to the tangent, to a tangent line. Same here. So if we take the cross product of these approximate tangent vectors, we get a normal vector. Now, this is something we've done with polytopes, a few weeks ago, when we did cross products of the PQ vector and the QS vector, or the PS vector. We get, excuse me, a vector that would be approximately tangent to the surface of the polytope. Okay, the upper surface of the polytope. So somebody's wanting to get in here. I'm going to let them in. So the slope of the let me greet this guy. Hello, Stephen. I'm doing a quick lecture, summary of a lecture from multivariable calculus. You're welcome to watch if you want. I've got to pin this video so I can see what I'm doing. Okay. Now, okay. So we have these sides, these slopes of the polytopes, these approximate tangent vectors to the surface, whatever f of xy is at this point. Take the cross product, you get a normal vector. Okay. Question: what's the slope, let's say, of, okay, the slope of this vector? Well, let's back up a minute. Slope of this vector is approximately equal then to the partial derivative of f at xy. Slope here is approximately equal to the partial derivative of y at xy, as we saw very recently. So if the slope is fx of xy here and fy of xy here, can we state a vector in this direction without actually going to the polytope, without actually having to calculate for a given delta x or delta y? In other words, this slope is the limit of what we get as delta x approaches 0, and this slope is the limit of what we get as delta y approaches 0. Okay. These are our partial derivatives. If we have the partial derivatives, and if you've seen from the recent assignment, it's easy to calculate partial derivatives if you can calculate derivatives. So we want to calculate the slope of, well, we want a vector in the direction of this vector, and we want a vector in the direction of this vector. So I'm claiming that the vector I plus fxk is in the direction of this vector. It'll have the slope fx of xy. Okay, well, what is the slope of the hypotenuse of the triangle that's formed by these two vectors? The slope is the rise divided by the run. The rise is fx, and the run is 1, because the length of the I vector is 1, and the displacement here is fx. So slope is rise over run, fx over 1, that's fx. That is the desired slope. So this vector has that desired slope. Now some people answered when we requested this that the slope was fxk divided by I. Okay, well, you can't divide a vector by a vector. There's no dividing a vector by a vector. So this is, well, this was originally written as fxk over I without the magnitudes. Now if we do fx times the magnitude of k over magnitude of I, that's okay. But fxk over I is not a correct answer, but it's the right idea. Okay, so we get fx for the slope anyhow. And similarly, we can do a vector, a j plus fyk is going to have the slope fy. So we get oh, well, I used the word exact there, but we want a pair of tangent vectors, so we can use I plus fxk over j plus fyk. Well, a picture of that, if we look at this from along the y-axis, might look something like this. You have the I vector, the fxk vector, the point. Well, the point up here is your xy, f of xy, this point. And from what we've done here, this hypotenuse is going to be parallel to your tangent line. Okay, going to have slope fx of xy. So we have a statement down here, vector I plus fxk is going to have initial point xy, f of xy. That point lies on the tangent line to the surface. Okay, this vector, that is, lies on the tangent line to the surface. So there we have it. Right there is the vector. It's on the tangent line. Okay. Another picture. Okay, if we look at this thing in a slice parallel to the xz plane, we have the point xy down here in the plane, delta x times the I vector here, and we project up to the surface. We have this point and this point on the surface. This plane will cut the surface in such a way that we have a curve up here. So we have this picture, kind of a local picture of a slice of the surface. You have a curve, you have your tangent vector. Okay, the vector is tangent to the curve at this point. It's tangent to the surface at this point. We can get a unit tangent vector just by dividing the I plus fxk by its magnitude. Similarly, with the j plus fyk, we can divide by its magnitude, and we get unit tangent vectors. Now, I arrived at a contradiction, and I haven't resolved that contradiction yet. Maybe in going through this, I'll see what I did. We want to talk about the meaning of the cross product of these two vectors. Okay, we have these two unit vectors. We want the meaning of their cross product. So it took us a while in discussion of this for people to come to much of a conclusion. So this is something that's you may be going to need to think about a little more. Okay, this cross product has to be perpendicular to both vectors. That's what cross products do. It's a cross product of unit vectors, so it should be a unit vector. Turns out it isn't, and I'm not sure what's going on. I don't want to stop and think about it. I've got another class in about 5 minutes. Okay, so this is perpendicular in any case to both vectors. What does the cross product say about the surface f of xy? It's perpendicular to both of these vectors. Both of these vectors are tangent to the surface in perpendicular planes. Okay, if we take the cross product, we're going to get something that's perpendicular to two tangent vectors. That's going to be a vector perpendicular to the plane, normal to the plane. Okay, so as somebody said, the surface is locally flat. That was a good comment, but we're still fishing around trying to get people to tell me a little bit more about this. But both of these vectors are in the direction of tangents to the surface. They're perpendicular. Their cross product should then be a vector perpendicular to the plane. So we do the cross product, and we have a picture here. Again, just reminding ourselves of the geometric situation. The I plus fxk vector unitized, the j plus fyk vector unitized. We relate that to the original polytope, and I'm not going to discuss that. That should be familiar to everybody because we've been doing polytopes to surfaces and so forth for quite a while now. Okay, so the cross product is normal to the surface. Thus, the cross product is normal to the tangent plane. It's normal to the surface, it's normal to the tangent plane. You need to understand that geometrically. Just go around looking at curved surfaces and put flat objects on them at different points, and you see a bunch of tangent planes. Okay, so we do the cross product, and that's a straightforward calculation, more easily done using the distributive law than the determinant, because these things work out pretty easily. So anyhow, we get this. These square roots are these square roots, and they don't work out, but I put them in there anyway. Looks like I've got 4 minutes. What can I do in 4 minutes? I think we can get through this, because I'm going to need these boards for my next class. Okay, so here's the cross product of the two vectors again. This denominator, this turns out not to be a unit vector, and I can't figure out why. Vectors are perpendicular, they're both unit vectors. We do the cross product, we get this. I know this is correct, but the denominator should be this. The Pythagorean theorem here gives you this magnitude, so I don't know what's going on. The unit normal, in any case, would be this. Okay, so what's the equation of the tangent plane? Well, the equation of a plane through a point, we need to understand geometrically. We can't just use a formula, we won't retain the formula. If we understand the geometric relationships, which are quite simple in this case, then we can do it. The geometric relationships come down to this. Here's a point, x naught, y naught, z naught. Here's a normal vector. Here's a point x, y, z. And here is the vector from x naught, y naught, z naught to x, y, z, and that's this vector. Okay, this vector has to be perpendicular to the normal vector. If the normal vector is ABC, then n dot this equals 0 is the equation of the plane, and I never used the ABC, so it was kind of redundant to write that, but this dot this equals 0 is the equation of the plane. You did use ABC in originally developing this a couple of weeks ago. Tangent, a plane perpendicular, plane normal to a given vector through a given point. That's something you know and you can easily do, I hope. Okay, so here's our situation again. Here's our point x naught, y naught, f of x naught, y naught. We're now calling this point x naught, y naught, 0. Okay, here are two tangent vectors. We take their cross product, we get a normal vector. So now we have I plus fxk cross j plus fyk. We're going to use this cross product rather than this one as the basis for our normal vector. Here's our normal vector. So at point x naught, y naught, z naught, the equation of the tangent plane is just, again, you take the normal vector dotted with this vector, set it equal to 0. Now that dot product is easy. The I component times the I component here, and I've got these in different forms, and of course you want to convert that, gives you negative fx times your x minus x naught. The j times the j component here gives you your fy times y minus y naught, both of these being negative, and then your k dotted with the, the coefficient here times this gives you your z minus f of x naught y naught equals 0. And at that point I need to stop, and then we're going to go on and actually calculate this for one of our familiar surfaces. And you see that once you understand the process, the calculation is really pretty straightforward and doesn't take all that long.